heat is in joules. It's a type of energy. Just to make a connection with something you might have heard of, if you've ever like shopped or looked at space heaters, the unit that they use is BTUs, stands for British Thermal Unit. I'm sure England has since abandoned that, but for some reason we're stuck in colonial times. So 1 BTU is equal to 1,055 joules. You don't need to know that. Just trying to make a connection with something you might have seen here in America. So give that one a shot. Have a conversation. Correct answer is A. That is it. Okay, it has a high temperature. A hot object does not have or contain heat. That is a popular misconception. A correct answer would be it has a lot of internal energy, but it does not have heat. Okay, heat is only the energy in transit from hot to cold. Good with that? Tell your neighbor. Correct answer is B. Heat or cold does not travel, heat does. From hot to cold. All right, so grab hands with your neighbor. Everybody grab hands with your neighbor. Reach across the aisle. Grab hands with your neighbor. Grab hands with your neighbor. Oh, it's not okay. I'm gonna get germs. Kids, that's what your immune system's for. All right, now I want you to figure out which way in each pair, which way heat is flowing. You feel, yeah.
I don't know. It's just me and
Okay, if you're holding on to someone's hand that feels cold, which way is heat going? From you to them. If you're holding on to someone's hand that feels warm, which way is heat flowing? From them to you. If you're holding on to someone's hand that feels the same temperature, you're at thermal equilibrium and no heat is transferred. You may drop hands. Okay. That was a bonding experience right there. I just feel closer. It's my physics family.
It's just written up there.
During COVID, that was a little awkward.
Yeah. Imagine someone got infected the next day. They're like, it was you. Tristan did a hand holding.
Y'all quarantined. Dirty bomb. All right. Is everybody good with A? It doesn't. They kind of just told you the answer previously. I did, straight up. Okay. Tell your neighbor. Tell them why you think so.
I did. I watched it.
Would you guess a refresher?
Correct answer is C. And reaches thermal equilibrium. Okay. Next question. Have a conversation.
I would think the other
Strawberry lunch.
I would think you would be.
I think it's strawberry milk.
But I below free. What's the cream course? Yeah. So neither. Yeah. If it melts, it's like it never melts, right? I think it was like 2 right, and they're both below 3%. He's not, but I feel like it.
Correct answer is
I'm not saying I don't know. D.
okay. Even if both objects are colder than even though both objects would be considered cold from our point of view, heat always goes from the hotter to the colder.
A.
So correct answer is it goes from the hot ice to the cold liquid nitrogen.
Hot ice.
Hotter than, I mean, look at that. That is really stinking cold.
Hot ice, that sounds really
It's so cool that, especially at first, it feels hot.
Right, burns you. Okay.
Why does that happen? Why does it feel hot when we touch something?
Our nerves don't know how to do that cold. So it's like,
They just die. They just die on contact.
they do. So, I mean, that's what you pour in warts. Liquid nitrogen.
Oh, yeah.
Freeze them off.
Good job, Mila.
Okay. This is not a trick question. This is just a baseline.
So, D. Cannot be determined. I don't like my coffee. Yeah.
Okay. Correct answer is A. But the warm-up question that was a warm-up question for this. This is the better question.
It's A. Stop it.
Have a conversation and tell them why you think so.
Oh, wait, internal. Sorry, I thought I had realized the question changed. Wait. Is it internal energy? Yeah.
No, there's more in that.
Yeah, there's more math. Oh, because yes, I remember that one. Should be proud. Yeah, that's an equation. Because it has more math.
No, I swear it's
Yeah.
Okay, so technically you might argue D, it can't be determined, but here's what I'm going for. I want you to say that the bathtub filled with lukewarm water has more internal energy. Okay, this is a good example of comparing and contrasting temperature and internal energy. This obviously has a higher temperature, which means there is the molecules, there's a higher average amount of kinetic energy for all the molecules in the hot coffee. Another way to say that is there's more energy per molecule in the hot coffee than there is in the lukewarm bathtub. But internal energy looks at the sum total, the collection of all the molecules, energies of that object. And because there's so many more molecules in lukewarm bath water than there is in a cup of coffee, that at some point is going to contribute more total energy than the coffee can. Does that make sense? Okay. So comparing and contrasting temperature and internal energy. Okay. Yeah, Mega.
So it was like the ice water. That would still have more internal energy, so it had more mass.
Great question. So that's why technically, unless I give you, there is a mathematical way to like calculate that, but I'm not. It's beyond the scope of this class. But yeah, at some point there's a trade-off. Stop. Okay, have a conversation.
Yeah, I'm looking. I've been unlocked.
Like, no, literally, you're being Good English.
Correct answer is
I don't know.
I don't know. I want to say.
I've heard every single one.
correct answer is D. Dangerous dinosaurs. Okay, so as you increase, as it gets hotter, obviously the temperature gets increased. Like don't like that's you're okay with that. Like that's that's true. You came into this classroom knowing that already. Don't get confused. Okay, now as the average amount of kinetic energy is increasing, so does the total amount of kinetic energy increases. That makes sense? So as something gets hotter, you can say definitively, yes, temperature increases, but also internal energy increases. Good with that? Tell your neighbor why you think so.
I think if I studied it.
I got it.
Oh.
I can say. Because I gave up. I was kind of curious.
That's all I
And then I did good. I was like,
Yeah.
I just feel like they set you up. Yeah. That's what I like to look at. Which is, what is that? I need to think of it. My teacher was saying that Purdue doesn't accept IDs.
yeah, that's fine.
I thought they did.
Which is fine.
All of my Spanish book credit is
Correct answer is? Correct answer is B. Copper. All right. Here's a couple. Try to make specific heat capacity like a thing for you that you understand. So one way is describe it as thermal inertia. So aluminum has a higher thermal inertia than copper does, so it doesn't want to change its temperature as readily. Okay, bless you. If they have the same amount of mass. Okay. Here's another way to describe it. Specific heat capacity. This kind of makes me think of like containers or buckets or cups. Okay. So like aluminum is going to have a certain size of a container. Each container represents how much energy is needed to change it by 1 degree Celsius. So let's say this is 0 degrees, then 1 degree, 2 degrees. How much energy is needed to change aluminum by 1 degree Celsius. The burner, the Bunsen burner, we could represent that like as a pitcher pouring in water that represents heat into this. And so this fills up. And when this fills up, it's like ding. Goes over here, starts filling up. Ding. We just change it every time it fills up. We change it by 1 degree Celsius. Okay. Versus copper has a smaller container. And so the heat is being poured in at the same rate. Ding, ding, ding. Like it's changing its temp, like it increases its temperature sooner, faster. That makes sense? Good? Have a conversation.
This summer we use I don't know what this means. Oh, I'm doing that.
That was a yes.
Correct answer is? Correct answer is D. Cannot be determined. Okay. You need to know you would need to know how much more massive it is. Okay. So this is what, the more mass there is, the more energy it's going to require to change the temperature. That's why this mass is here in this equation. Okay. If you think about it, when you're trying to heat water, regardless if it's on the stove or in a microwave, if you have a lot of water, that takes longer to boil than not much water. You all right with that? Takes more energy to add it to more water to get it to go to boil. Assuming you all have made mac and cheese at some point in your life. If not, like, go buy some mac and cheese and make it.
Last question, Mr. China. Get mac and cheese and a bank.
I mean,
Yeah.
Grab those two shorts.
And they quantify it and then you the bottom and say don't put microwave.
all right. Have a conversation about this question.
I see the word hung. I haven't. I feel like everybody. Oh. My goal every day. I'm usually a cheat back. A chunk.
Chunk. As
Did you, from like doing, did you do acid base?
No, yes.
have a conversation. Tell them why you think so.
Oh, really? No, it is. I never. I still don't. I still get I can't believe you're making.
Correct answer is it is below the halfway point. Why? Because water has a really big specific heat capacity compared to iron. Okay, actually about 10 times the. Okay, so here's the container analogy. So each one of these represents the amount of energy needed for 1 kilogram changed by 1 degree Celsius. This is the metal. This is the steel. There's 100 of these things. Okay. Water has such a high specific heat capacity, we're going to consider that like a 5-gallon bucket. Okay. So heat is going out of the hot metal into the cold water. Does that make sense? So in this analogy, what I'm doing is I'm taking the hot metal and I'm pouring heat from the hot into the cold water. So I'm taking these cups and filling up. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Ding. Actually, bing. It took that much. Filled up 1, 2, 3, 4, 5, 6, 7, 8, 9. Bing. We've only. So water has about 10 times the specific heat capacity as steel. So it's going to turn out to be close to 10 degrees Celsius. It's going to be the final equilibrium point. So have you ever seen movies of like blacksmiths working on horseshoes, and have it red hot, and then when they're done, they stick it into water, a bucket of water. That did not raise the temperature of water that much. Cool with that? Okay.
I don't know. Example, Lake Freeman.
Not totally, but
Close enough.
both are water. That doesn't. Have a conversation and tell them why you think so.
Wait, what is specific?
How much energy it takes to raise 1 degree Celsius.
Monday, Tuesday, Wednesday.
So it's how much energy it takes to make an object? Or
A kilogram, 1 kilogram of a material raise 1 degree Celsius.
I would say how much energy it is.
Actually, oh wait, A, B,
Correct answer is. Correct answer is higher A. Water has a higher specific heat capacity.
Oh.
So on a sunny day, on a hot sunny day, you're walking barefoot on the beach. Sand feels hot. Water feels comparatively cold. But at night, the sand feels cold. And the water feels comparatively warm, but really it's the same temperature it was during the day. Okay? Does that make sense? Okay? It takes a lot, water can take a lot of heat energy and not change its temperature that much. Okay? This is why the West Coast, California, Oregon, Washington, have more temperate climates than us in the Midwest, because weather systems come out of the west and go to the east. Okay? And so the warm fronts lose some of their heat to the water, and the cold fronts gain some of the heat from the water. And so their climate is more temperate. It's like the water is like a buffer, takes the edge off. Versus here in the Midwest, we have no big body of water to like help mitigate those changes. And so we can go from 80 degrees one day, quite literally below freezing the next. Okay. Oh yeah, totally. I feel like it just happened. I was wearing shorts and then I was wearing a hat and coat. Michigan, Western Michigan, actually has a more temperate climate because of Lake Michigan. Cool with that? Okay. Take a peek of that.
Oh. I was like, what are you? I'm here to correct me on my physics. I'm gonna correct you on your.
How could I make it better?
Or use that. And we're use that.
And were used. That's.
Gotcha.
Have a conversation.
Gotcha.
You got me.
Yeah. Everybody listen to the video. Mark down
Also, I want to get 7 points. Such a 10.
So, fun fact. Yes, it gets hot during the day in the desert, but it gets cold, like freezing at night. Used.
I'm having a graduate from I really don't want to at night, so I might not AC. Listen. You do? Yeah, because it goes from hot to cold.
That's fine.
So it goes, the heat goes from hot.
I'll send it on. I'll send it on.
So good. Good. I don't know. They should raise your SAT.
What's your name?
Wait, what food are you
Did you understand?
True to that.
Your name's like
That's why I
Oh
didn't
my gosh,
everyone else is regular.
the ACT, yeah. So you're having good food at like, I'm only going to
Oh.
I
Two.
Okay. Hopefully, your conversation sounded a little something like this. So, during the day, the adobe, the clay, has a high heat capacity, so when the sun beats down on it, it doesn't change its temperature that much. So it stays cooler. But over time, it does warm up. When the sun goes down and the temperature drops, it retains all that heat. Like it has a lot of internal energy, and because it has a high specific heat capacity, it's able to give off heat throughout the night and actually warming the insides, acting like a heater during the night. And then the process starts all over again. Pretty cool. Science. Yes. Sometimes it jumps out and gets you.
Don't get you.
It does. Have conversation.
Oh, wait, there's two.
No, you're good.
Okay, I remember this. I remember this.
doing
So Kogan's that's losing energy. So and then
Correct answer is B. Okay. So the hot object loses heat, the cold object gains heat. Good with that? Heat goes from hot to cold. Okay. Now, you might have done this in chemistry. Calorimetry.
I feel like you missed half the letter. Say it one more time.
Calorimetry.
Calorimetry?
Calorimetry. It's like calorie.
Well, yeah.
Calorimetry. Calorimetry.
See, that just don't help.
What?
Still spelled
Yep. Calorimetry.
I'm done. Sorry.
Okay. So the idea is we do this in an isolated or insulated system that no heat is able to escape. It's contained within. So ideally, the heat lost by the hot is gained by the cold. You all right with that? That's what we're going for. So here are some lists of specific heat capacities. Water has a whopping 4,186 compared to steel 448. Okay, about 10 times the difference there. Okay. So, example problem, if you have a 2 kilogram steel block that's heated at 80 degrees Celsius, dropped into a 0.5 kilogram container of water at 20 degrees Celsius, assume no heat from the system is lost. What is the final temperature of the water? Okay, so here's my thought here. So the heat lost by the steel is equal to the heat gained by the water. Okay. This is kind of the basis. Okay. Now, you could write it like this. You could say, bring that over, you could say 0 is equal to the heat of the water plus the heat of the steel. Mathematically, that might be easier to do, but conceptually, this is the idea. You all right with that? So, you could do it either way. So I'm going to incorporate this equation. So I've got, see this specific heat capacity of steel times the mass of the steel is equal to the final temperature minus the initial temperature of the steel. Remember, if you're doing it this way, to include that negative sign. Okay, that's the only hitch. That's the only catch to that. So it's equal to the specific heat capacity of water times the mass of the water times the final temperature minus the initial temperature of the water. Good with that? Okay. So how does the final temperature of the steel compare to the final temperature of the water? How does the final temperature of the steel compare to the final temperature of the water at the end of the experiment?
Same.
Why are they the same? Yep, they're going for thermal equilibrium. Okay, so these two things are the same. Okay, so just plug in numbers. So specific heat of steel is 448 times 2 kilograms times, okay, here's how I'm going to deal with this negative sign. I'm going to flip final and initial. So I've got, let's see, initial is 80 minus final temperature is equal to specific heat capacity of water, 4,186 times 0.5 kilograms. Final temperature minus 28 degrees Celsius. And there's a setup. Notice we have one unknown, final temperature. So now it's just an algebra problem. Then I'll bring all the T's to one side. The other was the other side. Yep. Yep. Why? Why did I do that?
Yeah, instead of like negative 80 plus, or does it not matter?
Oh, it's the same thing. So like if I make this negative and this subtract a negative, that makes that positive. So I just brought that over. I just flip. Do that. Notice, so the halfway point between 80 and 20 is going to be 50 degrees. You okay with that? Notice we're at 38 degrees. And that's even with 2 kilograms of steel versus a half a kilogram of water. Water has a really high specific heat capacity. Good with that? And that is the lesson for today.